much. Very good afternoon. So today I'm going to present Dr. Eamonn Keogh's next paper in this KDD, which is titled as Accelerating Dynamic Time Warping Clustering with a Novel Admissible Pruning Strategy. So this work is a joint collaboration with UT Dallas. So this is the talk overview. First, I'll be giving a motivation of dynamic time warping clustering. Then I'll be introducing a very new density-based algorithm, which people call the density peaks algorithm. Then I'll be moving towards our algorithm, which we call tadpole, or time series anytime DP. And we'll state what are the pruning strategies we have proposed, some experimental results, two very interesting case studies, and finally conclusion. So first thing is, why do we need to do dynamic time warping clustering? Okay, so typically in time series literature, people use the ubiquitous Euclidean distance measure, but there are many cases where there is a temporal lag between the objects. So for example, if you look at the top time series, which is in red, and the bottom time series, which is in blue, even if their shapes are very similar, but they are not properly synced in terms of time. So if you use Euclidean distance in order to measure the similarity between these two time series, then the distance is going to be very large, right? So dynamic time warping helps us to mitigate this problem. And it's a very old, like 40-year-old technique, and it's quality is very good, and nothing significantly beats this distance measure. Having said this importance of dynamic time warping distance measure, it's a toy example that demonstrates why do we need to do or use dynamic time warping to do clustering. So it's an interesting example that we have prepared for the paper. So we have three different mammals: cattle, whale, and mole. And we have the data of the mitochondrial DNA of these three mammals. So we converted this mitochondrial DNA to time series and clustered this time series with dynamic time warping and with Euclidean distance. And there was a ground truth that comes from the tree of life that states that the cattle and this whale, they have the same forefathers, whereas this mole is an outgroup. And this property has been captured perfectly by dynamic time warping, but Euclidean distance did not capture this property. This is because there are many mutations inside DNA, like insertions and deletions, which call the time series to be warped in terms of each other, which is perfectly captured by dynamic time warping, but not by Euclidean distance. So it's a demonstration that we actually, in real life data, need to use dynamic time warping to do clustering. Now, the question is, okay, DTW clustering is important, but why dynamic time warping clustering is hard? This is because typically in time series literature, if you want to do classification motive discovery, there is a common assumption that with increasing dataset size, there is a convergence of performance of dynamic time warping and Euclidean distance measure. So what do we mean by that? So on the left, we show an example in which we increase the size of the training set of a data set, and we perform one nearest neighbor classification, and on the y-axis, we are plotting the one nearest neighbor error rate. If you see closely, then you'll see that if the data set size is small, then the performance difference between Euclidean distance and dynamic time warping is huge. But as long as the dataset size increases, then both these actually converge. So no matter which distance measure you use, it doesn't matter. But the same observation is not true for clustering. So in order to show that, on the right, we do another experiment on the same data set, same set of data, and performed clustering to show that, okay, the blue line shows here the clustering quality. If we do the if we use the distance measure with Euclidean distance, and on top the red one is dynamic time warping. So as you see, even if the dataset size is increasing, the difference between dynamic time warping and Euclidean distance is not going away. So it means that, okay, the observation that the convergence of dynamic time warping and Euclidean distance will actually will be converging with increasing dataset size is not helping us in clustering. Okay, now I'll be giving an overview of the density peaks algorithm that we use in this paper. It has already received close to more than 40 citations, and it was published in very recently in 2014 in Science Journal. So the first question is, okay, why do we even need to use this DP or density peaks algorithm? Because we want to propose an algorithm, clustering algorithm, which is very parameter light, can handle arbitrary shaped clusters and insensitive to noise and outliers. And all these properties is beautifully captured in the DP algorithm. And the main assumptions that this algorithm makes are, the first thing is the cluster centers are surrounded by lower local density neighbors, and the cluster centers themselves are at relatively high distance with respect to each other. So what do I mean by that? If you look at the left figure here, you can see that different clusters are color-coded, right? Like in pink, violet, orange, and so on and so forth. So if you plot each of the points' density, and then corresponding to each of these points, if you want to find what is the minimum or nearest neighbor distance of these points that are staying at higher density, then you'll see these outliers coming out of it. And according to density peaks algorithm, these points are actually the cluster centers. And the idea is, the earlier you can select the cluster centers, the earlier you can achieve good clustering quality. Okay, so I'll be giving a very brief overview of density peaks algorithm. It works in 3 steps. First is the density calculation. Next is the nearest neighbor distance calculation from high density list. And the final is cluster assignment. Okay, suppose we are going towards the density peaks algorithm. The first step is the density computation. Suppose we have this small data set where we have these 3 different clusters, and the objects are lined up from 1 to 13 here. Now we want to calculate what is density, say, of object 1. So here I have zoomed in this figure over here. So if you see that we can think about a radius or a neighborhood around object 1 and count how many objects are within this pre-specified neighborhood. As you can see, this number is 4, and this number is written here. So for object 1, the number of objects that are within this neighborhood is 4, and this number is its density. And for all other objects, we compute this number. The next step is what is the nearest neighbor distance of object 1 from its high density list? So what do I mean by that? So here is object 1 with density 4. Now if you scan this whole list, you'll see that object 3 has density 6 and object 5 has density 5. So these 2 objects are at high density list compared to object 1. And if you look at the distance of object 1 to object 3 and object 1 to object 5, then it turns out that object 3 is the nearest neighbor, okay? So this is the nearest neighbor from high density list of object 1. And final step is the cluster assignment. So the cluster assignment works in this way. As I said, that the earlier you select the cluster centers, the better, the earlier you can get good cluster quality. So what would be the item 1's or object 1's cluster level? Because object 3 is its nearest neighbor from high density list, so whatever class label or cluster label object 3 has, object 1 will have the same one, and it goes like that. Now, our main contribution, the tadpole or time series anytime DP. The main beauty of this algorithm is it exploits both upper and lower bound of dynamic time warping. So as upper bound, we use the Euclidean distance, and as lower bound, we use the famous LBQ lower bound, which has been proposed from our lab. So it works in mainly 2 steps. First, we do distance pruning during local density computation. As I said, the density means how many objects are within some object's pre-specified neighborhood. Suppose we have this pre-specified neighborhood, which is this DC. Now we have this from top to bottom 4 exhaustive cases. So suppose this pathological case where I and J, these 2 objects are identical, then their distance is 0, so you don't need to compute the distance. What if you happen to be in this case, which is case B? So it means that the lower bound of I and J and the upper bound of I and J, they both are within this distance radius DC. So it definitely means that both these objects are within this pre-specified neighborhood, and you don't need to compute their distance. Whereas if you consider case C, where here already the lower bound is greater than this pre-specified neighborhood, then it means that both I and j are already at greater distance than DC, right? And the final case is only the ambiguous case, where you cannot say anything that anything from the lower bound and upper bounds. So the lower bound stays smaller than this distance threshold, and the upper bound is greater than this distance threshold. So only in this case we actually compute the distances. The next step is we do some pruning during nearest neighbor distance calculation from high density list. So I'll not be going into too detail, but I'll be giving a very high level overview of what we do in this step. Suppose we have item I here, okay? And from J1 to J4, these are all staying at high density list compared to object I. Now the question that we want to solve is, out of these objects, J1 to J4, which one is the nearest neighbor of I? And the trick that we use is we give an upper bound of the actual nearest neighbor distance. So how do we do that? We do this by making two passes within this data. First, what we do is we use the actual distances which are already computed from the density computation step and the upper bound to give this, and the upper bound of the objects to give an upper bound of the actual nearest neighbor distance. And having this upper bound, what do we can say? We can say that the nearest neighbor distance cannot be more than this bound, right? And so if it happens to be the case that in object I's nearest neighbor list, if any object has lower bound that is already greater than the upper bound that we have already defined, then definitely they cannot be nearest neighbor to each other. So we prune those computations. And so here also we do lots of distance pruning. Now having said that, okay, I'm saying that, okay, we do this distance prunings, but let's see some experiments that shows the quality of our pruning. So here is the experimental results. How effective is Tadpole's pruning? So here we take the Starlight Curves dataset, which is a very well-known dataset in time series literature. So we actually vary the number of objects in x-axis, and in y-axis we count how many distance computations do we have. So our obvious strawman to compute is the brute force DP algorithm, which needs the all-to-all distance computations to do the clustering. So as you see that with the increase of the number of objects, the brute force algorithm takes almost 7 million distance computations, whereas Tadpole has very few number of distance computations. You might be wondering, what do I mean by the oracle algorithm? The oracle algorithm is the one that takes into account only those distances that you actually need to do the clustering. So for example, as I showed, in DP algorithm, you have to compute the density and the nearest neighbor distance from high density list. So in order to do those, the oracle algorithm only considers the distances that actually makes difference. So the distances that you need to do the density computation and also the nearest neighbor computation during high density list. Of course, it's we obtain it by an expensive post-hoc study, but this is the best oracle that we can compete with. And as you can see that our algorithm, which is Tadpole, is very close to this very tough oracle algorithm. And on the right, in terms of the percentage of distance computation that we do, the brute force algorithm obviously does 100% distance computations, the all-to-all, whereas this Tadpole algorithm is very close to the oracle. And there is an interesting trend, like with the increase of the number of objects, Tadpole becomes closer and closer towards the oracle. Our another contribution is we frame our framework in an anytime fashion. So what we do is we propose a heuristic that finds the cluster centers earlier in the algorithm. So until the user interrupts, we can say that what is the current cluster quality. So as you see here, at least in this data set, after 10% of the distance computation, this Tadpole, which is in blue, is close toward, almost as good as the oracle. Of course, the Tadpole algorithm cannot understand that it has already achieved this cluster quality as good as the oracle, because here you can see that after this 6% of this distance computation, it achieves as good quality as the oracle. But after computing 10% of the distance computations, it actually realized that, okay, I have admissibly pruned the distances that I don't need to do the clustering, and finally I'm as good as the oracle. So having said that, having said that we have very good pruning from tadpole, we want to show that how good are actually the tadpole clusters. So in order to show the generality that tadpole is at least as good as the already proposed very well-known algorithms, we have compared tadpole with dynamic time warping, tadpole with Euclidean, with all the dynamic time warping versions of k-means, hierarchical, db-scan, spectral. And for different data sets, we have found that tadpole is almost as good as the proposed literature algorithms. So it's a very good algorithm which we can frame to do the prunings, and also it's also very amenable to be framed into an anytime framework. Finally, we have some very good and interesting case studies. The first case study I want to talk about is the electromagnetic articulograph. So in this data set, we have some subjects that have the sensors attached to their mouth, mostly in lips and their tongues, and they utter different words. And the task is to identify what words these subjects are saying. This application is interesting because suppose someone has speech disability, or someone just has done some surgery in their face, right? And then if he or she has some problem while speaking, it's interesting, it will be constructive if some algorithm can find out what he or she is trying to say. And it's a very interesting area of research these days. So we have this time series that are generated from the sensors, sensor accelerometers, and this is multidimensional data. And as you can see that these time series, they are clearly warped in terms of each other. So it's a very good data set to be framed and as a demonstration that tadpole is good. And on the bottom, we are showing the anytime figure here. So this blue plot comes from the tadpole ordering, and this green plot is from the oracle order. And as you can see that they are almost as good. And the next case study is the pulses dataset. So this is actually some disease which when you have this disease, you have some liquid form on the outer sac of your heart, and then it's a very threatening condition, and if you are not diagnosed early, then you are vulnerable to death. So people actually propose to use PPGs to cluster these data sets, and we have actually converted these PPGs to amplitude spectrums and clustered this data set using tadpole, and tadpole achieved perfect clustering quality and gave 88% pruning. So the conclusion. So here in this paper, we have proposed a generic clustering framework which we call tadpole, which exploits both the lower and upper bounds of the actual dynamic time warping distances and compute the clustering in an anytime fashion. And as usual, we have all the code and data available of this paper available at this website. And if you guys have any question, I'm very happy to answer. Thank you very much.
Thank you.
Hi, thanks for the talk. In one of the slides in which you compared your algorithm with the Oracle and the brute force algorithm, could you go back to that one, please?
Yeah, sure.
Yeah, this one. So on the left plot, we see that the tadpole algorithm actually, on the very less number of objects, it is below the Oracle. So what is the meaning of that?
It's actually not below the Oracle. It looks like that, but it's almost as close as the Oracle. It's, I mean, just because of the figure. It cannot be the Oracle. The Oracle is the best that it could have. Yeah.
Right, so that was my question. Like,
yeah. Right.
Is it exactly equal to it?
It's if the object size is small, it was exactly as the Oracle. Yes.
Okay.
Does the tadpole works when in the space has different density? The different clusters have different densities. Does it work?
Actually, it's a very good question, and that's why we use the density-based algorithm. Yes, if you have different densities, then tadpole will also work. But the crucial point is setting the neighborhood parameter, which is which is you use to define the densities of the objects, right? As long as you can tune this parameter perfectly for your data set, then tadpole works as good. So if you know that there are other density-based algorithms like dbScan, which has a neighborhood and mean points parameter, right? So the dbScan performs well if these parameters are well set, which is also the case for tadpole. So if you set this parameter right, tadpole is going to work.
Last question. I propose that we switch computers in the meantime.
Your clever idea for computing lower and upper bound seems to be applicable to other types of clustering algorithms, like K-means algorithm. Do you have any particular reason why you focus on this DP algorithm, except that it tends to have a good performance?
Yeah, that's a very good question, actually. So we didn't use algorithms like K-means because we wanted our algorithm